It is really my pleasure to introduce Roch Nianogo, who is an assistant professor in the Department of Epidemiology at the Fielding School of Public Health. He also is a former Rickmar Chimes Scholar, and his work has involved the application of innovative and rigorous epidemiologic and causal inference methods for investigating the impact of lifestyle, metabolic parameters, and social interventions in preventing chronic diseases such as obesity, diabetes, Alzheimer's disease, and other dementias, and translating these into effective clinical public health and policy interventions. Recently, he has collaborated on research projects aimed to investigate the importance of modifiable risk factors for Alzheimer's disease and other dementias. And so it's really my pleasure to introduce him and to have him share some of his methodologic expertise with all of us today. So thank you very much.
Of course. Should I go ahead and share my screen?
That'd be great.
Can you all see?
We can.
Fantastic. Wonderful. Thank you so much for attending this talk. It's my great pleasure to be able to share with you some of my knowledge on causal mediation analysis for identifying alternative intervention targets. And let's see if my pointer works. Okay. So today we're going to do it in about two different parts. The first one is we'll introduce some preliminary concept about mediation. And then secondly, we'll go into a little bit more detail about how to conduct mediation analysis, especially using a modern approach. And then we'll end with some concluding remarks. So why should we care about mediation analysis, and why is it important? I think. Okay, thank you. So for the last decade or two, there's been some rapid interest in the topic of mediation analysis, and there's been a lot of progress, especially by people like Robbins, Pierre, and Vanderwell, who have dedicated a lot of their careers to developing in the understanding of mediation analysis. It's become very interesting because as scientists, physicians, people become interested in mechanisms and pathways from exposures to different outcomes. It helps us to better understand the etiology, as well as to gain better etiologic mechanism and insight. The notion of mediation analysis is actually related to that of interaction, which we'll see in a bit, but it's important to distinguish the two. On the other hand, one of the reasons why we think it's really important to understand what causal mediation analysis can help us do is the fact that sometimes, especially in the area of intervention research, when we might want to intervene on an exposure, sometimes that may not be feasible or cost effective. And so mediation analysis allows us to quantify and identify different pathways that may be more practical or feasible to address. And so this is basically the essence of the talk today. So before we go into detail, let's talk about some preliminary different definitions. A mediator is basically a factor that intercepts the causal relationship between an exposure and an outcome of interest. So formally, if a factor affects a mediator M, and that factor also affects another outcome Y, then we can say that M is a mediator. And this can be readily seen when we use causal diagrams. Formally, this is called directed acyclic diagram, in short, DAG. And you can see here, we represent this by X is the exposure, M as the mediator, and Y is the outcome. So I think we're going to be using a lot of this way of graphing some of the relationship between the different variables and factors of interest so that we can communicate what we're saying in the different quantities. Okay, so let's talk about a brief example, and then we'll go into detail about how this actually works. So when we think about the relationship between race, ethnicity, educational attainment, and Alzheimer's disease and related dementia, there's some pathways and interesting pathways that we can think about. especially when we see, for example, that there's differences in cognitive performances or different risk in Alzheimer's disease across race, for example, between blacks and whites. We can ask the question, is this explained by different factors? One of them could be educational attainment. So there's been of interest the notion that there might be some possible indirect effect via education. And we can think about it this way. Race can influence education, which can influence other things like financial risk, medical access, dietary patterns, and so on and so forth until we get to an increased risk in Alzheimer's disease and related dementia. And so this is what we call indirect effect or mediated effect. There's another part of it that we call direct effect, for lack of a better word, but actually it's just the effect that is not mediated through the mediator of interest. And basically we could say that race directly influences Alzheimer's disease and related dementias, but on the other hand, this is just to say that it's all those pathways that are not through the mediator of interest. And this is really important because sometimes when we say direct effect, it's just because we're collapsing every other indirect effects that are not of interest at the moment. Right. So like I was mentioning in the beginning, this is very related to the notion of interaction and moderation. So what is that? So when an effect of a factor on an outcome varies across levels of another factor, we usually say that this is that the two factors interact with one another. This is also called effect measure modification or heterogeneity. So you can think about it, for example, if you have, if exercise, if for example, not exercising, for example, increases one's risk of heart disease by twofold. And that the risk, for example, is, let's say 2 for on the risk ratio scale for males, and it's about 1.2 for females, for example. We could say that there is a difference, right, in the level of risk, depending on whether you're looking at males or female, right? So this is an example of what we call moderation. And again, this is important because it's going to be, it's going to play a big part into, how we understand mediation. All right, so here, this is a small example to kind of see if we're following a little bit of how to actually depict the mediations as well as the confounding and other things. So in the first one, the first DAG, this is what we call confounding. So M here affects X, the exposure, and M also affects Y, the outcome, right? On the second DAG here, X affects M, which then affects Y. And there's also a direct relationship between X and Y, right? This is the classical example of mediation analysis. And this on the third one, the third DAG here that I'm highlighting right now, is actually a case where we talk about collider. A collider is basically when you have two factors like X and Y affecting one factor. So this can actually lead to a particular bias that we know as collider stratification bias. This is a form of selection bias. This basically just means that the sample in which you have restricted the individuals are no longer representative of the sample outside of that stratification. And this actually could lead to problem in spurious relationship that you may actually sign. And this is a key point that I want to mention and highlight because when we use sometimes some of the conventional method, this is something that is often overlooked. And in that form, as you can see here, this is where we represent a way to represent the interaction, right? See here, X basically is created by using the variable X and M, right? It's just a product of X and M. So we can include that in the diagram to show this right here. And this is actually interesting because when we do that, it allows us to see how many other pathways there could be between a particular exposure and an outcome. All right. So here, in the first case here, this is what we call full mediation, from X to M to Y. And then on the second part here below, is what we call partial mediation. So X to M to Y, but there's also another pathway that goes that does not go through M, right? So basically, these were basically the preliminary definitions that we have before we actually go into a little more detail. But please stop me if you have any burning question. I'll be happy to answer them as I go along. Now, the second part, which is still within the first subsection, is that we're going to be talking now about the differences between conventional and modern approaches to mediation analysis. I think about a month ago, we had a wonderful talk by Dr. Tor, I believe, on mediation analysis using different methods, convention method, Barron-Kini, structural equation modeling, as well as causal mediation analysis, right? So today we're going to highlight a little bit of some of them here and talk a little bit about some of the difference, and I'll now zero in later on the causal mediation analysis. So the way that I like to think about it is that there are two main approaches. There's one big one that we call classical conventional approaches. Under that, we have what we call a product method. So imagine that we were, for example, thinking about the effect of race on years of education, which and also why as the dementia, for example, here. Here we can see that one could calculate an indirect effect, at least using the product method, by first estimating the effect of X on M, which we call A here. You can think of it as a standardized regression coefficient. And then on the second stage, we could also calculate the effect of M on Y, and that we call B here. Again, you can think about it as a standardized regression coefficient. And then the indirect effect would just be calculated as the product or the multiplication of those two effects, right? So this is fairly simple, but as we'll see, there are some pitfalls here, right? For one thing, this works well, especially when we have a linear system. But then when it's not, the system is not linear, when we think about logistic regression, Poisson regression, it may not be as such, right? So this is just one particular thing here that we want to mention, but we'll see how other parts of this so-called conventional method breaks down. The second conventional method that we can think about is the difference method. This is very popular also in the social sciences. But basically, in this method, basically what we do, we first estimate the total effect, let's say, again, on race on dementia, right? And then we, in the second stage, we estimate what we call a controlled direct effect, basically, which is the effect of race on dementia, adjusting or controlling for the mediator. In this case, years of education. So as you can see here, you basically calculate the indirect effect as the subtraction between total effects, here D, minus the so-called direct effect C. So as you can see here, again, those are very appealing, fairly straightforward, but they can actually overlook some particular important notions. One of which, for example, that we talked about is, let's say you have some confounders actually between X and M, and then M and Y, right? But when you have that, by conditioning, stratifying on M, like years of education, looking, let's say, for example, between those who have more than a high school degree and those who have less than a high school degree, that can actually create a collider stratification bias, which would then lead to spurious results in the end. So those are the two main reasons why we actually are trying to maybe use another modern approach here. And I want to show that a little bit here by saying that actually these methods that I just presented, again, although they're very popular and very much used in the social sciences. And again, we have to note here that these methods have really, really been super helpful in helping us understand what mediation analysis is. Without them, it would have been very difficult to even think about how we think about it today, right? So you can think about it as the first step towards the understanding of mediation analysis, right? And so, but the problem with some of these methods that I just mentioned is that a lot of them actually ignore the possibility of an interaction, which we just saw in the beginning, between the exposure and the mediator, right? And that's really important. If, for example, the risk, for example, of a disease under a certain exposure varies by a lot of another factor, then the direct effect that we calculated is not going to be exactly what we think it is, right? Because there's going to be so many types of direct effect because of that interaction term. And we'll see how modern approaches, as well as conventional approaches, can lead to the same answer, especially when we don't have any interaction and all the other assumptions are equalized. The second point is that we can have a form of selection bias, what we call collider stratification bias. This is what I mentioned before when, for example, we were to control on M, put M in the regression model. That can lead to a bias, that is very similar to a selection bias. And then obviously, as in all models, we have the notion of uncontrolled confounding, meaning that you may have other confounders that you may not have thought about, you did not adjust for in your model, and this could lead to, again, a confounded response. And then lastly, one important thing here is that these methods are more great, especially when you have a linear system, a linear model, like a linear regression model, but not so well when you are now moving into the realm of a multiplicative model, like a logistic regression model, like a Poisson model, or other more complex model, right? So it's a little bit limited when we actually move beyond the linear system. All right, so that's why we are thinking about now using a modern approach, right? The modern approach basically is based on the counterfactual framework, and it allows basically the decomposition of a total effect into natural effects, right, and indirect effects. So natural just means the effect that it would attain under different scenarios, right? Under exposure status, under unexposure status, and things like that. That's what natural just means here. And another important notion about this modern approach is that it makes the assumption explicit. So we know that we're working within a framework that where we know the assumption, and we know that if any of these assumptions are violated, then our results are not should not be trusted, or at least we should interpret them with caution, right? So that's the modern approach. All right. So why do we think about the potential outcome? So actually, one of the main reasons why we think about that is ideally to be able to say that something is causal, we want to expose someone to a particular exposure or an intervention, and then go back in time and then expose the same person to that exposure or intervention or interest. We know that that's not possible, right? So that's why using a potential outcome framework helps us to define clearly in words and in mathematical terms what the ideal quantity of interest is. Here you can see a causal effect here is going to be the effect when exposed minus the effect had the person not being exposed, right? The same person had they not been exposed. That's what we call potential outcomes here. And then you'll see how that notion is actually important when we define some of the effects that we're going to be talking about when we talk about indirect effects, direct effects, total effects, right? So that's just basically a preliminary notion. So, in that same line, let's think about how to decompose the effect using the modern approach. Right now that we've said that we possibly a modern approach might be better than a conventional approach, then let's talk about how we actually break those down. Right. So the first step is to look at a diagram. Again, I use the diagram here, and again, just for didactic purposes, I think it'd be interesting to think about a particular exposure as opposed to just variable. Like, for example, we can think about X as adverse childhood experiences, M as psychological resilience level, right? High or low. And then Y as cognitive difficulty. And then XM is just the interaction between adverse childhood experience and a psychological resilience level. You can think about looking at the effect of adverse childhood events or experiences on cognitive difficulties by levels of psychological resilience, right? So that's basically how we can go about that. All right, so there are four basic effects when we think about the total effect and how we break them down. The first one, very important, is what we call the control direct effect, right? This is the effect that is due to neither mediation nor interaction. Basically, imagine that we have ACE adverse childhood experience that is directly affecting the outcome. And basically, here you will assume, if you will, that effect would not go through psychological resilience or would not interact with psychological resilience, right? So in other words, this is what we call it's the extent to which X cause Y when we make the mediator constant. So basically, when we set the psychological resilience for this to be the same for everyone in the population, right? That's another way of, if you will, fixing, setting, or making constant the mediator, right? And that's how we can calculate this quantity. You can see how that actually can have some interesting properties. The second basic effect here is what we call the pure indirect effect. A pure indirect effect is basically the effect that is only due to mediation. And I think I see someone who's asking to be admitted. So I'm just going to go ahead and do that. All right. And so the pure indirect effect is basically the effect that is due to mediation only. So imagine that the only effect that, in the only relationship between adverse childhood experience and cognitive difficulties were to go through psychological resilience, right? So that's the pure indirect effect, basically the extent to which adverse childhood experience affects cognitive difficulties via psychological resilience only. That's the pure indirect effect. And then we have what we call the reference interaction effect, RIE, which is basically the effect that is due to interaction only, but M is not caused by X, right? So again, this is the extent to which ACE, adverse childhood experience, cause cognitive difficulty only through its interaction with M here being psychological resilience. And then now we have the fourth and final basic effect, which is called the mediated interaction effect. This is basically the effect that is due to mediation and interaction, but M does not cause Y directly, right? So it's, again, going back to our example, this is the extent to which ACE, adverse childhood experience, cause cognitive difficulties only through its interaction with psychological resilience and through the mediation via psychological resilience, right? So again, those are the four basic quantities. You can see that here how by including the interaction term, we have been able to define different types of sub-effects here, which could be of interest, right? Right. So imagine one is interested in what we call the pure direct effect. Basically, that person would be asking the question, to what extent does an exposure X cause an outcome Y via pathways other than through the main mediator of interest? That's what we call the pure direct effect. And then we'll see that later and how that plays a part into the total direct effect. You can see here that that's basically the blue line plus the orange line here, okay? Now, let's say, for example, someone was interested in the question, to what extent does X, in the case here, does adverse childhood experience cause or increase cognitive difficulties via pathways other than through psychological resilience? But in this case, we allow psychological resilience, M, to be able to boost up or tune down such effect at the same time. That's basically just saying allowing for an interaction to happen, right? But this is just basically now going to be equal to the blue line plus the green line plus the orange line. That's why we call the total direct effect. You can see here that there's already a relationship between pure direct effect and the control direct effect because we have that mediated interaction that is basically added there, right? Okay, now we're going to be talking about the pure indirect effect, which we already saw. It's one of the four basic effects. And again, here it's just basically to what extent we were interested in the extent to which exposure X, ACE again here, cause cognitive difficulty via psychological resilience here M. And this is again the pure indirect effect. It's one of the basic effects here. All right. And one of the other important decomposition here is what we call the total indirect effect, right? And that total indirect effect is basically answering the question, to what extent does X, ACE, in this case, adverse childhood experience, cause cognitive difficulty via psychological resilience, here M, but here again, we allow M to boost up or tune down such effect at the same time, right? So, and as you might have already recognized, the total indirect effect is going to be equal to the pure indirect effect, which is the purple line here, plus the mediated interaction. So just something, if you pause here, we can see that something interesting is happening is that if there was no interaction, then a lot of these things will be equal to one another, right? If there was no interaction, if there's no XM relationship, right, then the PIE, or pure indirect effect, will be equal to the total indirect effect, right? So it's interesting, right? And so, so maybe we should have started here. So basically, if we ask the question, to what extent does X cause Y? To what extent does adverse childhood experience cause some difficulties in the cognition, in the cognitive function? So here we could see that one could be interested in just that total effects here, but we could also see that we can break that down into multiple effects, like the 4 basic effects here that we see here: control direct effect, and we fix the mediator to be the same for everyone in the population, the reference interaction, the mediated interaction, as well as the pure indirect effect interaction, right? So those are the 4 basic effects, basically, when you actually break down the total effect, right? So hopefully that's clear enough, and that allows you to understand the different parts that go into a total effect. All right. So by being able to do that, that leads us to being able to break down the total effect in many different effects, right? So we can do like a 4-way decomposition, basically by basically adding the different 4 basic components here: the control direct effects, the reference interaction, the mediated interaction, and the pure indirect interaction. We can also do like a 3-way interaction. Basically, we add in the pure direct effect plus the mediated interaction plus the pure indirect effect, right? So and so on and so forth, right? And I think that is also important, especially when we talk about the 2-way and direct effect. You can see here, this is equal to the pure direct effect, right, plus the total indirect effect, and those are going to be equal to the total effect, right? And we could have also like done it differently by adding the control direct effect plus what we call the portion eliminated. A portion eliminated is just basically anything that is related to interaction or mediation. That's what you see here, right here. So basically, the portion eliminated is anything related to interaction and mediation. And you'll see how that is important, especially as we talk about the example that we have together here. Okay, so another thing that is important is that, when we actually calculate these effects, the most important thing is not necessarily their quantities, but rather how, the proportion to what extent they contribute, for example, to a total effect, right? So one could be interested in the proportion of the portion eliminated, right? By just dividing the portion eliminated by the total effect, or the proportion that mediated, we just divide the total indirect effect, for example, by the total effect, or the proportion attributable to interaction. That could also be of interest, right? And we just divide the portion attributable to interaction by the total effect, right? So that's essentially how we break down different quantities, and we can actually sum them up together depending on what we want. And basically, that allows us basically to be able to be able to calculate different quantities of interest. All right, stop. What if there is no interaction between exposure and mediator? This is what I mentioned a little bit earlier. What happens then, right? And if we think about it, actually, it's actually interesting, right? So the pure direct effect is going to be equal to the total direct effect, which is going to be equal to the control direct effect, right? Because there's no interaction, right? So in such case, the conventional method will yield the same as the modern method if, and only if, all the other assumptions are exactly the same, right? We have a linear model, we have low uncontrolled compounding, and so on and so forth, right? So, but it's important that, there's a question sometimes that you hear, which is basically how do I know that there was an interaction? Well, in a lot of cases, your data won't be able to tell you. Well, you can always test for it, but as you know, you may not have sufficient power to be able to detect an interaction. You may be able to detect it if you have sufficient power, but if you don't find it, maybe it's just because you didn't have enough power. So because of that, you should always include an interaction term. And then because of that, then when you model, a signal may still be able to be picked up. And so you may have some substantial differences between pure direct effect, total direct effect, and control direct effect, right? So again, that's very important. So that's very important. Right, so now that we've outlined those 2 approaches, I think it's important to contrast them a little bit. So conventional method, like I mentioned before, they do not typically incorporate the interaction between exposure and the mediator, right? And this is done explicitly in the modern approach. In the conventional approach, the assumptions are generally not made or they're implicit, right? And I think especially in the era of reproducible science, it's important to be able to outline limitations and assumptions that we make by before connecting any analysis. So again, the modern approach helps us to make these assumptions explicit. So sometimes, unfortunately, when let's say we submit papers that are used mediation analysis, if you were to tell all the assumptions, sometimes the reviewers panic because they will say, oh, well, I'm not comfortable with you making all these assumptions. However, in a lot of cases, everyone actually makes those assumptions. Some of them are just implicitly made, but I think in the modern approaches, we made them explicit, right? So we need to train ourselves to be able to become comfortable making those assumptions explicit so that everyone can see. It's very transparent. Again, conventional methods, they typically apply to linear models, and modern approaches can be extended to nonlinear models like logistic, Poisson models, and others, right? Again, conventional method generally estimates one type of direct effect, one type of indirect effect. And again, like we saw earlier, you can estimate more nuanced effects, right? You can calculate a controlled direct effect, which is different from a pure direct effect, which is again different from a total direct effect, depending on the question, right? So you can phrase the question, or maybe the question just could be of interest to you, and then so these are different, right? Depending on what question you're trying to answer. And another thing that is important actually when you think about modern approaches is that the modern approaches do allow you to ask very nuanced and refined questions that may not have been able to be answered otherwise without these methods, right? So again, the conventional method may be limited or inadequate when you have complex scenarios like time-varying scenarios, when, for example, you have a confounder of the mediator outcome relationship that is also a mediator of the exposure outcome relationship. Then it becomes a problem. You don't know if you need to just treat it as a mediator or as a confounder. But modern approaches do allow you to treat them, both ways, but at different stages, right? So that's actually another advantage of the modern approaches. All right. Now that we've talked about all these different steps, we're going to go into the second portion of the talk, which is basically outlining how we actually implement that. First in an algorithmic fashion, and then we'll talk about some of the assumptions, and then we'll finish with an example and a practical example here, which I hope will help cement this concept of mediation analysis using causal mediation analysis. All right. Okay. So there are many methods. This is not one method to be used to implement and estimate indirect effects. One of them that I really like is called the G competition. But again, G competition is nothing more than standardization, but it's just standardization extended to time-varying exposures and factors. It makes use of regression models and simulation. It's quite powerful, and it can be extended to a lot of things, that we typically are dealing every day in our lives. For example, if you just want to standardize the estimate, you can use G computation. If you have time-varying exposures that are also confounders and mediators, you can use G computation. Right? And then we also like another one, which is called inverse probability of treatment weighting, which is the inverse of the propensity of being treated. This is also very interesting. It's very popular in medicine as well as in statistics. One of the reasons why I don't particularly like inverse probability of treatment weighting, especially when you have a longitudinal data set, when you have a lot of exposures, mediators, and basically many pathways. Sometimes what can happen when you want to estimate a different effect, you have to calculate first the weights, right? The weights for each of the pathways, and you have to multiply them together. So sometimes something can happen where some of the weights are so small that when you multiply them together, they become extremely small, and some people are overrepresented or underrepresented in the population, and that may not be as interesting. And you have the model-based approach, which makes use of regression models only. And in this one, you can think about it a little bit. It's a little bit the same idea of the structural equation modeling that we saw about a month ago. and also uses the idea of simultaneous equation modeling, which is great. Right. All right. So let's talk about now the confirmation analysis steps via G computation. And then I broke it down into 3 steps. And I think we should be able to implement them if we follow that recipe, basically. So the first one is, let's try to obtain the distribution of variables and relevant regression parameters needed for prediction or for predicting the counterfactual quantities, right? So the first thing, we get the appropriate distribution of each variable. All right, so imagine again our x variable as ace here. Here, imagine that we have, let's say, we dichotomize it. It's a yes or no question, for example. So here, all you need to get is just the proportion of those who have experienced adverse events during their childhood, right? You do that for all, for the exposure, for the mediator, and for the outcome. That's the first step. The second step is you regress. You model the mediator as a function of the exposure and the covariance. That's why a causal diagram is very important, because as you can see here from this diagram, we have M here, whose parent is X, or X, and Z, right? So those are the 2 arrows that go into M, right? By actually having that, I know that when I'm going to regress M, I'm going to regress M on X and Z, right? And same thing for Y, you're going to regress Y on everything that points into Y. First one is Z, second one is M, and then the third one is X. And as I was mentioning, this modeling approach makes use of the interaction between X and M, and so you would include that in your model. And this is what you have here. Mediator model is going to be X, Z here, and this is the regression coefficient here. You can think about it as alpha. And then you have the outcome model here, which is Y. And here you're going to have X, M, and Z, right? And again, imagine this is your data here that you have here, right? X is binary, Z is binary, M is not binary, but Y is also continuous, pretty much like M, right? So this is the first step, right? And I think we can do that. You can imagine already how you might be able to do it. Okay. The second step is the simulation portion, right? The simulation is basically when any software can do it, right? Any software that has a random number generator can actually implement this method. All you need to do is basically conduct like a simulation, which is basically like just that, you have the good thing is in different software you have already known distributions like normal distribution, binomial distribution. So you only need to use the function for, let's say, a normal distribution. Obviously, that makes you have to make the assumption then that, for example, the outcome is normally distributed, so that you can use, let's say, the mean of that outcome and the standard deviation of that outcome to simulate, to reproduce data that will have, let's say, the mean of your outcome and the standard deviation of your outcome, right? So that's what we call simulation. So you simulate the intervention and then the potential mediator and the potential outcome. So potential just means here, this is what we think that we'll have under a certain level of exposure or mediator. All right. So the first step is to stochastically predict, right? A new intervention variable, we call this X star, right? Just to differentiate it from the observed variable, right? And then this is an intervention or exposure that is independent of all covariance. It's really, really important because you want to make sure that the reception of the intervention. Imagine it's almost like a randomized control trial. So the reception of the medicine, the intervention, should not depend on different covariance. It should be completely random. So that's what you do. But to be able to do that, you have to know all the covariance, and we'll see how that you have to know all the covariance, right? So let's say here again you use a binomial distribution here. And then, secondly, you will stochastically predict the potential mediator M star using the regression parameters obtained above and the new intervention variable X star and based on covariance, right? And again, you get M star, alpha M plus alpha X star plus alpha ZZ and the epsilon M, which is basically the error in the prediction, right? And then you stochastically predict the potential outcome Y star using the regression parameters obtained the above, and then it obtained above, as well as the new intervention variable X and the new mediator variable M star in the baseline covariance Z, right? Again, This is basically, again, everything when you did your regression on the step above, all you have to do is just collect those regression coefficients, and then you just basically put them here so that you can predict your Y, right? So you see, all these things are parameters that you've already estimated or you just recently simulated. And so depending on whether you are interested in the pure direct effect, total indirect effect, and so on and so forth, all you have to do is to change the value of X at different stages. So for example, let's take the pure direct effect. So in the pure direct effect, the value of X, which is the exposure, will be 0 at the M stage, but at the Y stage, it's not going to be, it's just going to be X, just like the random variable X that you have simulated already, right? And then you have the M0 here, it's important. The M0 here is the M0 here that you predicted under the no intervention exposure, right? So basically, you said, assume that people did not get that exposure, and so their M becomes an M sub 0, which meaning a potential M had they not received the intervention. And now to calculate the Y, you just use that M0 here, where whenever you have M in the regression model that you have already estimated above, you just take that value and you plug it there. And as relates to X, X is a total random variable. It's basically here the new X, the X target that you just replace it with. That's basically what you do. And at the end, what you would do is you would fit what we call a marginal structure model, meaning that you would fit a model in which you don't have any other covariate in the model, right? This is what you have here. You would just fit the last stage, the regression, Y star as a function of X star. That's it, right? And then depending on whether or not you wanted to estimate a pure direct effect or total direct effect and so on and so forth, then you will be able to choose them accordingly, right? And then whatever you're going to be regressing it on, you're basically going to give you the theta X here is basically the estimate of interest. That's if you use Y underscore PDE, then theta X is going to be the pure direct effect. If you use Y underscore PIE, then the theta X is going to be the value for PIE, which is the pure and direct effect, right? And so here, this is a diagram again showing how our hypothetical intervention, again, remember when I was saying here that you're going to be predicting a new intervention that is independent of all the covariates. That just means that we're assuming that we can randomize the value of X. And then by doing that, then we basically take away, so basically we take away the relationship now between Z and the new X, which we call X star, all right? So hopefully that was clear enough, but that's basically the different steps in implementing a causal mediation analysis via the G computation, which is basically a standardization approach, right? So by doing the simulation, just integrate across all background variables, all the Z's and things like that, right? All right, so now let's talk about the explicit assumptions and then we'll finish with the example here. Again, like I was saying, it's important to recognize that in the modern approach, basically an additional thing that we do here is actually that we make the assumption explicit. And the first one is that we assume that everyone is exchangeable in the population after we have adjusted on the common confounders, covariates. So basically, we should be able to take two individuals who have, one is treated and one is untreated. And then within that sample, basically, they should have the same, like if you look up the average age among treated or those who have the intervention, and the average age among those who do not have the intervention or the treatment, they should be roughly equal. Imagine it's like a randomized control trial, basically. When you implement the intervention, you expect to have covariate balance between the different covariates, right? Like age, sex, and all the background factors. This is basically what that assumption means. It just means that after you've accounted for the known covariates, then they should be exchangeable. All right. And to go down a little bit into detail, that just means that there should be no confounding between the exposure and the mediator. There should be no confounding between the mediator and the outcome. And there should be no confounding between the exposure, and the outcome, right? This is what we term here. There should be no U1, no U2, and no U3. Another type of confounding here that we typically say that it should not be there, but we can still estimate it under different circumstances, is that the equation where the instance where I was telling you that imagine L here. L is both, as you can see, a mediator, because you have X, L, and Y, and X, L, M basically is, you can think of L as a mediator. At the same time, L is a compounder of the M-Y relationship, right? So that could be a little bit of a problem, but not to worry. There are methods to be able to estimate such effects. Now we don't call them natural effects; we call them path-specific effects, right? But again, this is we can put a star on this particular assumption, because it's still possible to estimate it. Again, here, I guess this is exactly what I was just saying about the fact that you cannot estimate natural effects, but you will be able to estimate path-specific effects. Right. The second assumption, beside the uncontrolled confounding, is the positivity, basically covariate support. This just means that if you were to stratify the exposure by a particular variable here, let's say C, let's say age group, you should not have a zero cell, right? Basically, for example, if you think of here exercising 150 minutes per week, for example, and then, let's say age is, C equals 1 is age group 80 plus, and C equals 0 is age group less than 80. Let's say, for example, you were to have this particular example, you see that, there's a very small likelihood that maybe people who are over the age of 80 are still able to do 150 minutes per week, right? So that's basically to say that maybe in your data, you won't have anything here, right? And that's basically saying you won't have covariate support, right? So basically you need to have that probability to be different than 0, meaning you need to have some people here, right? Consistency just means that the effect, when you implement an intervention, the effect of the intervention on the outcome is only due to the intervention itself. It should not be due to how the intervention is being administered. Imagine, and this is the classical example, is what we call the white coat effect. If you were to go, for example, in doctor's office, maybe by looking at the everything in the office, white coat and all that, that will maybe increase your blood pressure, or maybe because someone, if the doctor gives you medication, maybe there will be a better effect, right, than if, for example, your friend gave you that same medication, right? So here, this is saying that it should be consistent, right? Regardless of who gives you the medication, the intervention, it should give you the same thing. Interference just means that my outcome, whatever outcome I have, should not depend or affect anyone else's outcome in the population, right? And this is obviously validated in infectious disease scenarios, right? So, but it's important to think about here. And obviously, no other sources of bias, no selection bias, no measurement error, no model form is specification, right? So this is kind of important to think about, because it's great to be able to make those assumptions so that we don't actually there's no problem in the interpretation. All right, and we finish now with an example. So here, imagine Jennifer Weave and others have been able to conduct wonderful, fantastic research on cognitive function decline, as well as the incidence of Alzheimer's disease and dementia. And one of the questions, they're interested in a lot of things, but one of the questions that we're interested in is, to what extent years of education explains the black-white disparity in cognitive performance, right? And this is the causal diagram here: race, years of education, and cognitive performance in older adults. And so basically what they found here basically is that the, compared to whites, black perform less well on cognitive assessments, right? And the direct effect here just means that, this is the estimated effect of race on cognitive performance through pathways other than those involving years of education. Again, here, this shows that there might be other pathways through which race affects cognitive decline. And again, here, this means that there's a negative effect, basically, for blacks compared to whites. The control direct effect is, imagine in the population, if we were to set everyone, we were to make constant the variable years of education to make it equal to 12 years for everyone in the population, right? What would be the reduction, if you will, of cognitive impairment or decline? And this is what we get here. And again, you can see here already that there is, by setting everyone to, let's say, 12 years of education, you can see that this is reduced a little bit, right? And so another effect that is important before I get into the percentages is that you have the indirect effects here. The indirect effects here, again, this is the estimated effect of race on cognitive performance through pathways involving, let's say, years of education, right? And this is being, ad hoc estimated because it was not estimated in the paper. But basically, what does this mean? Well, this means basically that 17% of the, if you will, the disparity might be explained by setting, the years of education to 12, and you may be able to even reduce the disparity by, let's say, or said it another way, if you were to set the years of education to 12 years for everyone in the population, you would basically reduce the gap, if you will, by 17%. Another important quantity here is called the proportion needed through education. Again, this is just calculated as using the total indirect effect by the total effect here, and this is about 35%. Right. All right. So I'll finish here with my last slide. I'm sorry, I think I might have gone a little bit over. But here we want to say in conclusion that mediation analysis is actually very essential in for understanding and quantifying mechanisms and pathways from an exposure to an outcome. It is very critical in disparities research, and it's very important in helping identify alternative targets, and perhaps those targets that are more feasible and more cost effective. Again, the intuition, I think, is a little bit straightforward, but it's important to understand what question, right? So we go back to that research question, what it is that you want to know, what is that a question of interest, and then from that point on, we can move on to estimating those quantities. And again, recent work has been able to help out to estimate what that is, and there are even software to be able to implement these. Again, like I mentioned, you don't need a specialized software, but I typically prefer using that because using common softwares that have a random number generator like SAS, R, and others, because it makes it a little bit more flexible because you may have some scenarios that are not necessarily included in different packages, right? These are the references that you can check out. And there is actually a package that have been created for this particular purpose, and it's available in R. And basically, it's very helpful if you want to use it. I use it sometimes to just verify my results, but for the other portion that I like to just do it on my own. That way I have a little more control of what goes in. All right, I want to stop here and thank you very much for your attention. I hope it wasn't too fast and that you were able to get a little bit of knowledge in this particular presentation. Thank you very much, and I'll take any questions if you have it.
Thanks so much, Roch. That was great. So we've got a couple of minutes here for questions. Luisa, do you want to ask your question?
Yeah, no, thank you so much. Great presentation. Looking forward to go through the slides later. And yeah, because it's a really good way to show, racial, ethnic, and gender disparities, right? And how you can show these gaps, related to other factors. So I love it. But my question, have you done this on Stata?
I think in Stata it's possible to do it. I haven't done it in Stata particularly, but it's, as long as there's a random number generator in Stata, it is possible. It's just the algorithm can be implemented in any very software. If you just follow the different steps that are outlined here in the PowerPoint, you should be able to implement it as well.
Thank you. Thank you so much. Very interesting work. Thanks for sharing.
Yeah.
Other questions? Oh, Ron Hayes has a question.
Yes.
Yeah. So I may not be getting the letters right, but when you're talking about the interaction between X and M, I believe that's the way you described it. You said that you should always test for that. And
The
what?
opposite.
What? Sorry?
You should not necessarily test for it.
Well, I mean, you should include it, you said, right?
Oh, yeah, okay, exactly.
Oh, yeah. So isn't there, so I didn't say it right, but isn't there a time that you would not want to include it? There's, because you're saying you may not have enough power to detect it, but couldn't it be just noise to the system, like in standard regression, where you don't want to include things that are not really contributing? And don't you want to be able to at least conclude, yes, there was, or there wasn't an interaction?
Yeah, that's a very good point. I think from practice, usually what happens is, because we're not really estimating. So basically, by including it in the model, you're actually not going to be obviously in the pre-processing, because on that first stage where you include in the regression model, right, in the step one, you actually you don't really care about the value of that interaction, right? Because at the end, when you use your simulation, you're just going to be able to use those coefficients and just simulate. And at the end, actually, where it's more important, you're not even going to include that again, right? So the only reason why we include it is because there may be some signal, very small, that you may not be able to pick it up. But because you're not, again, interested in that per se, it may still come out in the final stage when you fit your margin structure model. So to say that again, basically, we should not necessarily test for the interaction, because you may not necessarily have enough power. However, there may be still some small signal that may still be able to go through interaction, and as such, you should always include it, and then go through the steps, and then obviously if you were to run the simulation and all that, and there is it's basically the same thing, the pure direct effect, the total direct effect, and the control direct effect, then obviously you might be able to see that maybe there's not that much interaction, but I think in practice, Tyler Vanderbilt has recommended at least that we include it, because there may still be some small signal that may still be able to go through when you do the simulation.
All right, thank you.
Yes, Dr. Bell?
Tom, I know you have a question, but we have another talk starting at 4:15. So is it a quick question?
No, go ahead, but just to tip of the hat to Roch for laying out a lot of the underlying assumptions. I was just going to ask about sensitivity analysis strategy, so I'll just put it out there as a question broadly, but we maybe just leave it there.
Yeah, thank you very much. I think that's very important, and I think even in the package that I mentioned, the CMS verse, they actually include like some options to do sensitivity analysis for when you have uncontrolled confounding of the different relationships, like calculating e-values and things like that. But that's really important to be able to test the strength and the robustness of your intervention. Thank you very much for the question, and we can certainly chat about it afterwards as well.
Sounds good. Thank you, Roch, for the talk, and thank you, Tom, for coming. It's great to have you here.